I want you to imagine moving into um, a brand new, sleek, just absolutely minimalist apartment. You know, you've got the floor to ceiling windows, the clean lines, polished concrete floors, the works.
Sounds pretty nice, honestly.
Right. It's gorgeous. But then, for some completely inexplicable reason, you insist on dragging along this 500-pound antique grandfather clock.
Oh, no.
Yeah. It takes up a quarter of the living room. It requires constant maintenance. It scratches the floor. And here's the kicker. It doesn't even keep the right time anymore.
But you keep it anyway, right? Just because it's always been there.
Exactly. You keep it simply because you've always had a clock, so you just feel like you need it.
It basically becomes this localized black hole for your space and your energy, you know? It completely undermines the whole modern environment you just built around it.
Yes. And that 500-pound clock scratching your floor,
Right.
in the C++ world, that is CPP Coro.
Yeah, that's a perfect analogy.
Today, we're looking at this incredible masterclass in software engineering minimalism. It's a 2026 presentation by a developer who goes by the handle at Look036.
Right, and it's a fascinating one.
It really is. We're going to deep dive into the migration of C++ coroutine generators from that bloated legacy library, CPP Coro, to a hyper-streamlined modern solution called Pi2CPP.
Which is such a massive shift in thinking.
Our mission for this deep dive is to unpack how stripping away over-engineered code doesn't just, save some disk space. It fundamentally transforms how safely and quickly a program executes.
Okay, let's unpack this because I'm super excited.
Yeah, I mean, the broader philosophy here is really critical, especially today when we are constantly bombarded with information and just really complex frameworks.
Absolutely, the overload is real.
Right. So understanding the architectural why behind the code we write and recognizing when an accepted industry standard has, secretly become technical debt, that's a skill every single engineer needs to hone. Because we just hold on to legacy patterns out of sheer momentum, right? We never actually stop to calculate the true cost of keeping them around.
Exactly. We just assume someone else figured it out and it must be optimal.
Well, let's calculate that cost by looking at the burden of over-engineering in CPP Coro. The presentation gives this highly specific post-mortem of the library, and honestly, the dependency chain alone is staggering.
Staggering is definitely the word for it.
They highlight this single file called config.hpp that spans 177 lines, and its entire existence, its only job, is dedicated to detecting the compiler, the operating system, and the CPU architecture.
Right, and the culmination of all those 177 lines of heavy lifting is a single, almost trivial binary decision.
Wait, all that just for one decision?
Yeah. It's just to decide whether the library should include the standard coroutine header or the older experimental coroutine header.
It's like buying a universal remote with 1,000 buttons, but you literally only want to use it to turn on the TV.
That is exactly what it is.
But wait, isn't that kind of robust checking standard practice? Like, why is this specifically such a problem here?
Well, what's fascinating here is that historically, yes, robust environment checking was standard practice. When C++20 coroutines were still just a technical specification and not, fully adopted, libraries absolutely needed those fallbacks.
Right, they had to cover their bases.
But standardizing a feature means we're supposed to drop the scaffolding. Holding on to a 177-line detection block in a modern code base creates this massive processing burden for the compiler.
Oh, because it has to read it every time.
Exactly. Every single time a developer includes the generator, the compiler has to parse that massive block of macro soup.
Which just kills build times.
It does. And it creates an equally massive cognitive burden for the developer, too. The presentation illustrates how this bloated configuration file forces a pattern of severe architectural indirection.
What do you mean by indirection in this case?
So if you're trying to debug a generator, you cannot simply open generator.hpp and just read the logic. The implementation forces a mental stack trace.
Oh, I hate that.
Right. You jump from generator.hpp, you cross over into coroutine.hpp, and then eventually you are dumped into that 177-line config.hpc maze. The actual mechanism of generating a value is just completely obscured by all these layers of defensive abstraction.
It's like hiding the actual engine of the car under 6 different locked hoods. And from the source material, this over-engineering bled directly into the mechanics of the coroutine itself, didn't it?
Oh, completely. The presentation dissects how CPP Coro handled pointer yields using std.address off value.
Okay, and why is that dangerous?
Well, In a standard synchronous function, passing references around is relatively safe because the call stack strictly guarantees the object's lifetime.
Right, it knows when the function ends.
Exactly. But coroutines are asynchronous, they suspend execution.
Ah, which introduces massive risk, I'm guessing.
Huge risk. If you yield a reference to a temporary variable inside a coroutine, and then that coroutine suspends, the temporary variable goes out of scope. It's gone.
So when it wakes back up,
When the caller eventually resumes the coroutine and tries to access that yielded value, they are reading garbage memory. It creates a dangling pointer.
wow. And that leads to those subtle, non-deterministic bugs that take like weeks to track down. The worst kind of bugs.
The absolute worst. And it doesn't stop there. CPP Garo also utilized this incredibly convoluted design just to figure out if a sequence was finished.
Like just to check if it's at the end of the list.
Yes, instead of just a simple Boolean check, true or false, it implemented entirely separate sentinel types. They built a generator sentinel type, which then mandated 4 different operator overloads to handle constant and non-constant comparison.
Wait, 4 different overloads just to ask, are we there yet?
Yes, it is a massive state machine built entirely to ask the program, are we out of items yet?
That is wild. And the source actually breaks this down mathematically, right? Which just perfectly illustrates the grandfather clock analogy from earlier.
Yeah, the numbers are pretty damning.
It says the legacy CPP core generator required 187 lines for the core logic, an additional 35 lines for coroutine support, and then those 177 lines of configuration infrastructure. That totals nearly 400 lines of code.
Yep.
But the replacement solution, presented by Lux036, it accomplishes the exact same task in just 97 lines.
It's incredible. The old standard was mathematically about 4.1 times more complex than it needed to be.
That is a massive bloat factor.
And when Lux036 saw that bloat, the realization wasn't just to refactor CTP Coro, it was to aggressively sever the dependency chain entirely.
Just throw the whole clock out the window.
Exactly. And that philosophy birthed PyGenerator. Going from 400 lines down to 97 lines with literally 0 external dependencies is just an incredibly bold architectural statement.
So how does PyGenerator actually pull that off?
Well, it operates on the assumption of a modern compliant C++ setup. It strips out all that configuration boilerplate, directly includes the standard coroutine header, and immediately gets to work.
Clean and simple.
Very. Furthermore, it retains full support for reference types, but it does so using a really straightforward pointer-based storage system. It completely bypasses all those convoluted sentinel overloads we were just complaining about.
That reduction in code complexity is honestly brilliant. But, and this is a big but, we really have to discuss the most polarizing design choice in this entire migration.
Ah, yes, the exception handling.
Right, because this fundamentally shifts how we even think about safety in C++. In the legacy library, if an internal error occurred, like an exception was thrown during the generation of a value CPP Coro, store that exception using std.exceptionptr.
That would hold on to it.
It would hold on to it, suspend the coroutine, and then literally rethrow that exact same exception at the next iteration site.
Which feels safe, intuitively.
Yeah. But the new PyGenerator scraps that entirely. If an unhandled exception occurs, it simply calls std.terminate. It intentionally crashes the whole process.
Yep, hard crash.
Here's where it gets really interesting for me, though. std.terminate literally aborts the program. Isn't catching and throwing exceptions the proper way to handle errors? Like, why would we want to intentionally crash?
Well, if we connect this to the bigger picture, it sounds dangerous until we actually examine the underlying mechanics of what std.exceptionptr demands from the system.
Okay, walk me through it.
When an exception is thrown in C++i, the one-time has to allocate memory for the exception object. Capturing that exception inside an asynchronous coroutine, type erasing it so it can cross execution boundaries, and then passing it back to a caller who might be on a completely different thread.
That sounds heavy.
It is. It forces the compiler to allocate that memory dynamically on the heap.
Oh, wow. Which means if you are yielding a sequence of, say, 1,000,000 integers, you are forcing the system to pay a heap allocation tax on every single coroutine frame.
Exactly. Solely to prepare for an error that will probably never even happen.
So you are basically destroying your cache locality and execution speed for an illusion of safety.
I'm glad you used the word illusion because I use it deliberately here. A generator is fundamentally an input iterator. It represents a sequential conveyor belt of values.
Okay.
If the internal body of that generator throws an unhandled exception, the generator's internal state is compromised. You fundamentally cannot recover mid-sequence.
So if the conveyor belt snaps, catching the exception and attempting to pull the next item doesn't magically fix the belt.
Right. You have no idea which items were damaged, which were skipped, or what state the internal variables are in. Catching the exception just allows corrupted data to quietly slide into the rest of the application.
Which is terrifying, honestly.
Calling std.terminate is a highly calculated trade-off. By aborting the process immediately upon an unhandled exception, you achieve two major things.
First being performance, I assume.
Yes. First, you remove that massive dynamic allocation overhead from the hot path of your generator, which drastically improves performance. Second, std.terminate produces a pristine immediate snack trace.
So you know exactly what went wrong and where.
Exactly. You are prioritizing predictable, loud failures and high performance over an expensive and frankly dangerous attempt at recovery.
If this breaks, I refuse to pay a performance tax to hide the breakage. I mean, that is just a fascinating way to approach software resilience.
It really is.
But, if paying a performance tax for error handling on a single generator is bad, paying it recursively has got to be catastrophic.
Oh, it is a nightmare.
And this presentation tackles that too, right? The deep tree dilemma. When a generator needs to yield another generator, like, for example, traversing a complex abstract syntax tree or a deeply nested file directory, the memory management just becomes a nightmare.
Yeah, standard recursive generation scales terribly. Let's say coroutine A yields coroutine B. The system has to keep coroutine A alive and active in memory, holding its place, while B executes. If B then yields C, now A, B, and C are all active simultaneously.
It reminds me of like a rigid corporate ladder. If a frontline worker identifies a problem and needs a decision, they have to tell their manager, who tells the director, who tells the VP, who tells the CEO.
And they're all just waiting on the line.
Exactly. You have 5 layers of highly paid management consuming resources just to pass a single message back and forth. And in C++ terms, the presentation notes that for a tree structure with a depth of 1,000 levels, standard recursive generators force the system to maintain 1,000 simultaneous heap-allocated coroutine frames.
Which is ridiculous. The application will likely crash from memory exhaustion long before it ever finishes the traversal.
Right. So how did they fix it?
Atluck03dex solves this using a specialized tool called Pi Recursive Generator. It implements a really elegant computer science concept known as symmetric transfer.
Symmetric transfer. Okay, so if the issue is the nested hierarchy, the only mathematical way out is to basically flatten it, right?
Yes, precisely.
So symmetric transfer essentially gives that frontline worker a direct walkie-talkie to the CEO, allowing all those intermediate managers to just step completely out of the execution path.
That's a great way to visualize it. Technically speaking, symmetric transfer leverages a specific feature in the C++20 coroutine application binary interface, the ADI.
Okay, getting to the weeds. I like it.
Normally, a wait suspend returns void or a Boolean. But if a wait suspend returns another coroutine handle, it instructs the compiler to bypass the traditional C++ call stack entirely.
Wait, really? It just skips the stack?
Yep. It tells the processor, do not resume me, just transfer execution directly to this new handle.
So it is essentially a tail call optimization specifically designed for coroutines. The parent frames don't hold the execution hostage anymore?
Exactly. The promises are chained together into a flat linked list, and the root's pull method simply walks that chain upward as generators complete.
Wow.
Only the loof node, the specific branch that's currently doing the actual work, consumes active processing focus.
That is so clean. And the empirical results from the presentation's depth tests really illustrate the magnitude of this optimization. They ran a test on a recursive chain of 100 nodes.
Let me guess. The standard generator failed miserably.
Well, a standard manual loop generator behaved exactly as expected. It kept 100 frames alive simultaneously, suffering from massive O-depth memory copying overhead.
Just burning through memory.
Oh, yeah. But the Pi recursive generator, utilizing that symmetric transfer, kept exactly 1 frame alive at a time. It successfully converted an exponential O-depth memory nightmare into a flat O1 memory overhead per yield.
It's basically magic.
The depth of the tree became entirely irrelevant to the memory consumption. I mean, that's just an incredibly elegant application of the C++20 standard.
It is. But, theories and big O notation are intellectually satisfying, sure. But the true metric of any architectural shift is the actual migration.
Right. Does it work in the real world?
Exactly. Many elegant minimalist theories completely shatter when they are actually forced to integrate with legacy code bases.
Well, the good news is the data provided on the migration completely proves the stability of this approach. They tested this across multiple live projects. The first was Digraphics CPP. They migrated two core files from the legacy CPP Coro to the new Pi2 CPP generators.
Yes.
And interestingly, they also took this opportunity to switch their build system from CMake to XMake.
Oh, that makes so much sense. Moving from CMake to XMake perfectly aligns with the minimalist philosophy of the entire presentation.
Because CMake is so bulky.
Oh, CMake is notoriously complex. It is arguably the 500-pound grandfather clock of C+ build systems. XMake, on the other hand, is Lua-based. It offers significantly faster dependency resolution and just much cleaner syntax.
Well, the transition was completely seamless. All 38 tests in the Digraphics suite passed on the very first run.
That's impressive.
Right. And then they applied it to a much larger project, Egin CPP. This one required migrating 6 header files and 6 source files, which included swapping out the old recursive generators for the new symmetric transfer pi recursive generator.
A much bigger test then. How did it do?
45 tests were run, and 45 tests passed.
Zero regressions. That is the most critical takeaway here. It proves that the new Pi2CPP API is robust enough to act as a nearly drop-in replacement, despite fundamentally altering how memory, recursion, and exceptions are handled at the lowest architectural levels.
Yeah, the final tally across Pi2 CPP, Digraphics, and Agent was 117 tests passed with 0 regressions. And get this, the migrated codebase replaced 400 lines of entangled CPP Coro infrastructure with roughly 340 lines of total Pi2 CPP code.
Wow.
And that 340 lines includes the implementation for both the standard generator and the recursive generator.
It's just a complete win. And the qualitative improvements are just as impactful as the line reduction.
Oh, for sure.
Because the compiler no longer has to parse hundreds of lines of configuration macros for every single translation unit that includes a generator. Build times just drop significantly.
Right.
The codebase itself is inherently clearer. It utilizes fully qualified types without the ambiguity of all those legacy namespace directives.
And above all else, they successfully severed the dependency chain. There are 0 external dependencies tying the projects to an outdated library now. It is a complete vindication of the developer's strategy.
Completely.
By questioning the accepted norms, by utilizing direct pointer storage for references, by prioritizing predictable crashes over that expensive illusion of exception picture recovery, and by flattening recursive execution with symmetric transfer at Lux 036 proved that simpler architecture almost always yields superior performance.
It's brilliant. And the specific migration is a technical case study, sure, but the underlying principle scales to almost any complex system.
Right, it's not just about C++ star.
Not at all. Whether you are architecting a microservices backend, organizing a corporate structure, or just designing your own daily workflow, the most profound efficiency gains rarely come from adding new tools.
We always want to buy the new app or framework.
Which is due. But the real gains come from ruthlessly auditing your dependencies and pruning the bloated configuration files of your own processes.
It is about finding the 177 lines of useless config in your own life and just having the confidence to hit delete.
Hit delete and don't look back.
So I want to leave you with a final thought to ponder today. If a widely used established library like CPP Coro was secretly hiding a 4x bloat factor and massive memory inefficiencies simply because everyone assumed the standard tool knew best.
It makes you wonder.
It does. What other foundational tools or assumptions in your own industry are secretly dragging down your performance? What is the 500-pound grandfather clock sitting in your workflow right now, just waiting for someone to look closely and build a 97-line replacement?